Welcome to G Fun Facts Online. The universe is a vast, silent ocean, and for most of human history, we have only been able to see the foam on the waves. We see the stars, the galaxies, and the glowing gas that make up what we call visible matter. But beneath this luminous surface lies the deep, dark currents that drive the cosmos. We call it dark matter. It is the invisible scaffold of the universe, outweighing visible matter 5-1, yet it has evaded every attempt at direct detection. We know it is there only by its gravitational ghost, the way it spins galaxies and bends light. But the era of seeing is ending. We are entering the era of listening. With the advent of gravitational wave astronomy, we have gained a new sense. We can now hear the vibrations of space-time itself. And in these ripples, generated by the most violent cataclysms in the cosmos, lies the potential to finally illuminate the dark. This is the story of how we are using the crash of black holes to map the invisible architecture of the universe, specifically the dark matter halo. To understand how we hunt the invisible, we must first understand the quarry. Dark matter is not merely a filler in the universe, it is the foundation. Every galaxy we see, including our own Milky Way, is embedded within a massive, spherical cloud known as a dark matter halo. Imagine a galaxy not as a spinning disk of stars floating in emptiness, but as a small, glowing gem frozen in the center of a vast, invisible iceberg. This iceberg is the halo. It extends far beyond the visible spiral arms, composed of particles that do not reflect, absorb, or emit light. They interact only through gravity, and perhaps the weak nuclear force. These halos are not smooth, featureless clouds. Computer simulations, such as those using the Navarro-Frank-White or NFW profile, suggest they have complex structures. They are densest at the center, known as the cusp, and they taper off towards the edges. They are also likely clumpy, filled with smaller subhalos or mini-halos that swarm around the galactic center, like bees around a hive. For decades, we have mapped these halos using light. We watch how stars on the outskirts of galaxies orbit too fast, held in place by the halo's invisible grip, or how the halo's gravity bends the light of distant galaxies through gravitational lensing. But these methods are static. They measure the halo's effect on things that are already there. Gravitational waves offer a dynamic probe, a way to measure how the halo interacts with matter in motion. One of the most exciting predictions of dark matter theory is the density spike. At the very heart of a galaxy often sits a supermassive black hole. As this black hole grows, its immense gravity pulls the surrounding dark matter halo inward, compressing it into an incredibly dense spike or dress surrounding the event horizon. This region is the ultimate laboratory. Here, dark matter is compressed to densities trillions of times higher than in the solar neighborhood. If we could probe this region, we could unlock the secrets of what dark matter actually is. But light cannot escape the black hole, and the dark matter doesn't shine. This is where gravitational waves enter the stage. In 2015, the LIGO observatory made history by detecting the first gravitational waves, ripples in the fabric of spacetime caused by the merger of two black holes. Einstein predicted these waves a century ago, but their detection changed astronomy forever. Unlike light, which can be blocked by dust or gas, gravitational waves pass through everything. They are pristine carriers of information. When two compact objects, like black holes or neutron stars, orbit each other, they churn spacetime, radiating energy in the form of gravitational waves. This loss of energy causes them to spiral inward, eventually colliding. The waveform of this signal, which is the shape of the wave over time, tells us the masses, spins, and distance of the objects. But here is the key. The waveform also encodes the environment. If two black holes merge in a perfect vacuum, the waveform follows a precise prediction from general relativity. But if they merge inside a dense dark matter halo, the environment drags on them. The signal we receive on Earth will be slightly different. It will be distorted, shifted, or dephased. By detecting these subtle anomalies, we can weigh the invisible medium they pass through. The most promising method for detecting dark matter halos via gravitational waves involves a scenario known as an extreme mass ratio inspiral, or EMRI. This occurs when a stellar mass black hole, perhaps 10 to 50 times the mass of our Sun, is captured by a supermassive black hole, which is millions of times the mass of the Sun. As the smaller black hole orbits the larger one, it travels through the dark matter spike, that ultra-dense dress of invisible particles we discussed earlier. As the small black hole moves, it wakes the dark matter. Its gravity pulls the dark matter particles toward it, creating a wake of higher density behind it. This wake exerts a gravitational pull backward on the black hole, acting like a frictional drag force. This phenomenon is called dynamical friction. Think of it like a spoon stirring honey. The honey resists the motion of the spoon. In the cosmos, the honey is the dark matter halo, and the spoon is the orbiting black hole. This friction steals energy from the black hole's orbit. Consequently, the black hole spirals inward faster than it would in a vacuum. It merges sooner. For a detector like LISA, the Laser Interferometer Space Antenna, which is scheduled to launch in the 2030s, this effect is observable. LISA will watch these EM rise for years, counting hundreds of thousands of orbits. If dynamical friction is present, the gravitational wave cycles will slowly drift out of phase with the vacuum prediction. Over a year of observation, the accumulated dephasing could amount to thousands of radians, which is a screamingly loud signal in the data. By measuring this dephasing, scientists can calculate the density of the dark matter spike. If we find these spikes are common, it confirms the cold dark matter model. If they are absent, it might imply that dark matter particles annihilate each other, destroying the spike, or interact in exotic ways, forcing us to rewrite physics. While dynamical friction probes the dark matter inside the merger, gravitational lensing probes the dark matter between the merger and us. We are familiar with gravitational lensing of light, describing how a massive galaxy cluster bends the light of a background quasar, creating arcs or multiple images. Gravitational waves can be lensed too. If a wave from a distant merger passes near a massive dark matter halo on its way to Earth, its path will be bent. Light has a very short wavelength, so it treats halos like geometric lenses. But gravitational waves have enormous wavelengths, sometimes thousands of kilometers long. When the wavelength of the gravitational wave is roughly the size of the lensing object, a phenomenon called diffraction occurs. This is similar to how ocean waves bend around a barrier, or sound waves bend around a corner. If a gravitational wave encounters a small, compact dark matter halo, a mini-halo roughly 1,000 to 1,000,000 solar masses, it will diffract. This diffraction creates an interference pattern in the signal received at Earth. As the frequency of the gravitational wave changes or chirps during the merger, the interference pattern shifts. This allows us to probe subgalactic dark matter structures that are completely invisible to telescopes. Finding these mini-halos is crucial. The standard cold dark matter theory predicts thousands of them should exist in our own galactic neighborhood. If we don't find them, dark matter might be warm, meaning it moves too fast to clump efficiently, or fuzzy, implying quantum mechanical waves on a galactic scale. Furthermore, if a gravitational wave passes a very dense compact object, like a primordial black hole or an ultra-dense dark matter core, the signal might be split into two. Because the two paths have different lengths, we would hear the chirp of the merger twice. We would hear the main signal, followed milliseconds or seconds later by a fainter echo. Detecting these echoes in LIGO or Virgo data would be a smoking gun for compact dark matter structures. There is also a wilder hypothesis to consider. What if dark matter isn't a particle at all? What if it is made of primordial black holes? These are hypothetical black holes formed in the first fraction of a second after the Big Bang, created not by dying stars, but by the collapse of ultra-dense pockets of hot plasma. If they exist, they could constitute all or part of the dark matter. Gravitational wave detectors are the ultimate tool to test this. If dark matter is made of primordial black holes, these ancient black holes should be merging constantly. One clue is subsolar mass mergers. Stars cannot collapse into black holes smaller than about 1.4 solar masses, known as the Chandrasekhar limit. If LIGO detects a merger involving a black hole with the mass of a planet or half a sun, it must be a primordial black hole. This would solve the dark matter mystery overnight. Another clue lies in high redshift mergers. The Einstein telescope, a planned third-generation detector, will be able to see mergers from the cosmic dawn at redshifts greater than 20 before the first star is formed. If we see black hole mergers happening before stars existed, they must be primordial. We can also look at the eccentricity signature. Black holes formed from stars usually orbit in circles. Primordial black holes, whizzing around in dark matter halos, would often capture each other in chaotic, highly elliptical orbits. Detecting a population of mergers with high eccentricity would strongly point toward a dark matter halo origin rather than a stellar origin. We are standing on the precipice of a revolution. The current detectors, LIGO in the USA, Virgo in Italy, and KAGRA in Japan, are being upgraded. But the real game changers are the next generation observatories. LISA, launching in the mid-2030s, will be a triangle of lasers spanning 2.5 million kilometers in space. It will be sensitive to low-frequency waves, exactly the frequency of supermassive black holes and EMRIs. Its target is detecting the dark dress spikes around galactic centers, and its promise is measuring the particle mass of dark matter by how fluffy or cuspy the spike is. Then there are the Einstein Telescope and Cosmic Explorer. These are proposed underground detectors with arms tens of kilometers long. They will be 10 times more sensitive than LIGO. Their target is detecting millions of mergers per year, back to the beginning of the universe. Their promise is mapping the distribution of mini-halos via gravitational lensing statistics and hunting for primordial black hole populations. We also have pulsar timing arrays. By watching the rhythmic ticking of pulsars, which are neutron stars, astronomers have recently detected the hum of the gravitational wave background. This background noise is likely caused by the slow and spiral of supermassive black holes merging throughout cosmic history. The shape of this background spectrum depends on the friction these giants experience, giving us a measure of the dark matter density on the largest scales of the universe. While the prospects are thrilling, the path is difficult. The signal of dark matter is often a subtle distortion, and there are imposters, for example, baryonic matter. A regular accretion disk of gas around a black hole can also cause drag or dynamical friction. Disentangling the drag of gas from the drag of dark matter requires precise modeling. However, gas usually flattens into a disk, while dark matter stays spherical, leading to different orbital precession effects. Another challenge is waveform modeling. To detect a deviation from general relativity, we need to know the predictions of general relativity to incredible precision. Theorists are currently using supercomputers to calculate template banks of waveforms that include dark matter effects, so we know exactly what to look for. For centuries, we have stared into the dark, trying to glimpse the invisible scaffolding of our universe. We have seen its shadow on the motion of stars and the bending of light. But now, the silence is broken. The detection of invisible mass via gravitational waves represents a paradigm shift in cosmology. We are moving from inferring dark matter's existence to probing its material properties. Is it a fuzzy wave, a heavy particle, a swarm of ancient black holes? The answers lie in the chirps, the echoes, and the dying breaths of colliding black holes. The dark matter halo, once a silent ghost, is about to speak. And when it does, it will tell us the story of the missing 85% of our universe. We just have to keep listening.